Good afternoon, everyone. Thank you for watching our group meeting today. And today we'll have a presentation by Mikael about bosonic dark matter through white dwarf mass measurements. So let me put here.
Vou dar um zoom aqui. Is it okay?
Yeah, I say good.
Okay. So, hello everyone. Good afternoon. I'm Mikael, and today I'm going to be presenting about this paper, which I think was published on Archive last week, which is entitled "Testing Bosonic Dark Matter Through Wide Dwarf Mass Measurements." It's not a type of paper that we usually present here because it's not model building or theory, but rather it makes some concepts of cosmology and astrophysics to basically tell us, hey, if you have a model of bosonic dark matter as a complex scalar field, maybe it's something testable because we have a problem when we try to measure white dwarf mass. Basically, what's the main goal in this paper here? Basically, nowadays, we have two different ways of measuring white dwarf stars measurements. We have the electromagnetic method, which is the method in which we use spectroscopy, photometry to find some properties of the white dwarf, such as the superficial gravity, the radius, the temperature, and we can infer its mass by some expressions, but it's something model dependent. And we have other way of finding the white dwarf mass measurement, which is the basing on redshift. We know from general relativity that whenever you have a gravitational potential L, when light tries to escape this potential L, it will lose energy, it will change its color, and will suffer from a gravitational redshift. And also from this, you can infer the mass of the white dwarf star. So that we have those two different methods. But the main problem is that they do not match. This is a big problem because we have two different measurements and they do not usually match. So what they do here in this paper is that they explore an alternative way, which they include a complex scalar field, which is invisible to electromagnetic interaction, aka the telescope will not be able to detect it using electromagnetic measurements, but it will contribute to the mass of the white dwarfs because it's a massive scalar field. This is the main idea. And what they will reach in this paper is that the fraction of this scalar field, which is basically dark matter, right? The definition of it is 5 to 15% of the total mass in this range. So this is basically what I just said now, the two different ways to measure it and the fraction of dark matter. So basically, this is the problem. I just told you the problem. And the main motivation for them to work with bosonic dark matter in this case is that they say in here, scalar boson stars arising as solutions to the Einstein-Klein-Gordon equations are stable, horizonless, and transparent to light, making them viable dark matter candidates. So this is the motivation why they are choosing specifically bosonic dark matter, not other type of dark matter. Okay, so they start with the theoretical setup. First of all, whenever you have a massive body, you basically in cosmology use the Einstein field equation, which is this equation in here. As you can see, the Einstein tensor and the stress energy tensor in here. But we have two different systems now. We're supposing a scalar, a complex scalar, which is invisible to light, and we have this visible part. So we have two different stress energy tensors. The first one for the visible part, whenever I say visible part, is the part of the white dwarf star without considering this additional scalar field. And it's this one as follows. This equation you find on most of general relativity books. And this is for the visible part, in which they assume a polytropic approximation, in which the pressure is proportional to the density to the power of something. This is the first approximation that they choose here. It's called the polytropic approximation for the visible part. This is the stress tensor for the visible part, and for the invisible part, which is the scalar part, is this one in here. So we have those two different stress tensors. As you can see, of course, it depends on the potential of this field, but they say here in the paper it's given by basically proportional to the mass square of the field. So it's our free parameter of our model. Okay? But basically, what's the main goal in here? We are trying to look for spherical solutions, and we are also interested in static solutions. Why? Because our main goal here is to, given a white dwarf star, I want to know the amount of mass which is related to the dark matter, and the mass contribution which is related to the visible part of the white dwarf. Okay. So basically, they find the equilibrium equations as being those ones. As you can see, the Einstein equation, just like I said, the total stress energy tensor is the contribution from the visible part and the scalar field. The derivative of the potential, and of course, the derivative with respect to the energy tensor. Those are the equilibrium equations of our system. This is the equilibrium for our whole system. Just like I said, we are looking for static solutions. I will explain this in the next page, but we are looking for these stationary solutions. And of course, it should be also spherically symmetric. So the element of line is given by this. As you can see, it does not depend explicitly on time, because B and A, which appear here in the metric, are metric functions and depend only on the radial coordinate. And last but not least, they do the ansatz for the scalar field as being this one, in which omega here represents the oscillation, the frequency oscillation of the scalar field. Okay, so from those equations, they derive these equations here. Of course, I'm not going to explain one by one, but the main idea is, from this system and these approximations that I'm choosing, I can have an expression for the total mass of my system, which is this one in here. This is the total mass of the system. But there isn't much we can do with this type of mass, because our main goal is to find the contribution for the invisible part and the visible part. So this just gives us the total mass. So how can I find the contribution for the other parts? We have to find the numerical approach, and more specifically, in general relativity, whenever you have a system that's stationary, and of course also fit other conditions, but mainly stationary, the mass of this system is given by a common mass, which is this expression in here. It's an integration all over a hypersurface, in which this is the Killing vector. Okay? So what's the advantage of doing this? Because you can rewrite this expression here to be dependent on the stress energy tensor. But hey, I have two different contributions for the energy tensor. So now I have two different integrals. I have one for the white dwarf star without dark matter, and the invisible part, which is this one. That depends, of course, on the potential, which is proportional to the mass square, our free parameter. This is great because this is basically what we wanted, right? And the total mass, of course, is the sum of the two. And just giving a brief review on the two different methods that we usually do in astrophysics. But basically, the electromagnetic method consists in which you calculate the surface gravity, you calculate the radius, and you calculate this temperature. But this temperature is strongly dependent on model. So we'd say that's model dependent. It gives you a value of mass, which is this one. This is the mass that you find using this method. And using the method for the redshift, there's this other expression in here. And just like I said, they do not match. As we can see in this graph in here, they have got a sample. And from this sample, as you can see, the black little dots in here, they represent the electromagnetic measurements. and the blue ones that represents the redshift one. As we can see, for small radius, they do not match. As you can see, the error bar is incredibly large, especially for the redshift method. But for larger radius, they mostly coincide, in which the paper says that probably when it comes to, let me say here, the one they put here, we explore equilibrium configurations motivated by the observed 5% to 12% discrepancy between mass estimate derived from those two different methods. Okay? So great. Just like I said, we have two different methods and they do not match. And this is the problem. We try to, as a solution, we try to add this new field, which is a scalar field. And first thing that they do is they show this table in here. But basically in this table, we have the real data, which is those columns in here, and we have our model. Just like I said, we have a free parameter, which is mu, the mass of the scalar. And for each different mu, you find different masses for the visible part and the dark matter. And the contributions are those ones in here. And this is very important. This is one of the most important parts of the paper. Why? Because, for example, they chose a mass in the range of 10 to the minus 10, 10 to the minus 11, 10 to the minus 11. But if you choose, for example, 10 to the minus 15, then probably this will be 0.000 something. So they say that it's not something detectable. And in the model that they are building, the best values, as we will see further, are the values on 10 to the minus 10 and 10 to the minus 11 for this model. Okay? This is the first thing that they show in here. Just like I said, note, this is basically what I said now. Note that the bosonic particle with a mass far outside this range would not generate configurations with observable consequences for the white dwarf. This is basically what I said. If you try to put 10 to the minus 15 here, this is not going to be something detectable. Okay, great. And they show figure two, basically for completeness, the radial profile and the pressure profile for the model that they are working with, which is this figure in here. Those two figures in here, let me just zoom out a little bit. And just for completeness, just like I said, we will have different pressure profiles and field profiles depending on the mass, on the dark matter. But basically, this is just for completeness, okay? But the analysis is the same. Okay, great. But I think one of the most interesting plots on this graph is this one. If you take a look at this one, what does this graph represent? Basically, if you see here, let me zoom in more, not zoom out. If you see here, for example, it's the radial of the white dwarf, and here's the total mass. Here's the visible part. And this gradient of color basically represents you the fraction on dark matter contribution to the total mass on the white dwarf star. As we can see, most of the sample that they have chosen have a good good fraction, which is around 0 and 20%, but we have a little problem in here with this white dwarf, which is the Sirius B. They explain it. They say, okay, this is the limitation of our model. As you can see, for example, in the gradient of color, somehow orange in here, it represents 30 to 40% of dark matter contribution, which is, of course, something absurd. And they say this because the method and the polytropic approximation that they have used is not valid, it's not a good approximation for a smaller radius. And as you can see, this is a very small radius compared to the other ones. And again, the blue one represents the redshift, and the black one represents the electromagnetic method. But it's for a fixed, of course, fixed value for mu. This is basically what I just explained. In particular, our model assumes a polytropic with a fixed index, which, while effective for many white dwarf configurations, may introduce some limitations for extreme cases, such as this one. Which one? The smaller radius, the Sirius B. Okay. And last but not least, they have this other graph in here in which they basically consider the difference on mass on the real data and the difference in mass on the model that they have built. This delta M here represents the real data, those black dots in here, and delta M with T represents the model. They're basically the same. We have two different delta M's. Let me go back to the table. We have this minus this, which is the real data, and we have this minus this, which is the model. And they're basically comparing them to see if their model is viable. Here. And as you can see, most of the data in the model they match, but for smaller radius again, we have this incredibly large error bar, which is the serious bit again. And yeah, this is it. Just to finish, they do the model selection, data analysis. They do some Bayesian statistics. Basically, they choose the likelihood. And what they do here now, just mathematics, I'm not going to explain all those things. But basically, the main goal in this part in here is given the real data, what's the best value for mu? This is the main idea in this part here. This is why they plot this table here. This is something you can do with likelihood. Given the real data, what's the best value for mu? If p is less than 1, that's probably not a good value for mu. But if it's 1 or larger than 1, then this is a viable value. And as we can see, most of the values that are larger than 1 are 10 to the minus 10 and 10 to the minus 11, just like we wanted to. Oh, sorry, just like we have showed on all of the graphs, we fixed mu 10 to the minus 11, 10 to the minus 10. And basically, this is it. This is the paper. Again, just to summarize, we have two different ways of measuring white dwarf star mass, the electromagnetic method and the redshift method. They do not match. How the papers try to solve this include a new scalar field that will contribute to the mass and will be invisible to electromagnetic interaction, basically dark matter. And they analyze if the model that they are building, they match with the real data. This is the main idea of the paper. Thank you so much. This is it. Yes, questions?
Why do we use the spherical metric for distortion?
Oh, basically because we are looking for a spherically symmetric solution. The white dwarf star is spherically symmetric. So basically, this is the reason. No. Vai, Patrício. Patrício.
Okay. At some point, you said that a white dwarf with 20 30% of dark matter was absorbed. What is that?
I think because for that value on the 40% contribution of the white dwarf star, you have a delta M that is too different from the delta M of the real data.
Oh,
For me, it's not very clear how they interact, how the interaction between the scalar field and the bosonic star happens. Basically, because of the metric of the.
Well, I think, I might be wrong, but I think they did not go deep in the discussion in this paper.
They just put some type of stress energy tensor for the scalar field for the bosonic star.
Yes.
And in principle, the idea is that inside the dwarf, white dwarf, there's dark matter, that's the scalar field. That's the main idea. Or I understand.
Basically, from the paper, it's actually the other way around. It's surrounding the white dwarf. Yes.
Okay. So they can surround it. All right. I think something interesting to look at is probably interaction between the scalar field
Mm-hmm.
and I don't know the rich scalar of
Okay.
the metric of the Schwarzschild-like metric.
Yeah.
They consider some type of non-minimal couple.
Yes. Oh, that's a good.
Would be,
Yes.
something interesting to look at, but I don't know if it's gonna give some very robust results.
Oh, I see. Yeah, but I think it's a good idea. Yeah, that could be.
I think they are just gravitationally bound. That's it.
I mean, but if there's some no minimum cut,
Okay.
so I mean, in principle could change something, but I don't know if it's going to violate some symmetry or it's going to be a very weak effect. And
No, what I say is the scalar that matter just
surround-
gravitate.
Yeah, surrounding the.
That's why it's surrounding. It's like the situation with the galaxy. The
Yeah.
dark matter halo is surrounding because the dark matter gravitates, and the baryonic matter also gravitates, but dissipate energy. I think here we have the same situation, but in a smaller scale.
Why cannot be fermionic? You comment something about.
Oh, it's not that it cannot be, but the main motivation for the choose the bosonic one is this one. I think it's on the next page. Give me a second, please. Here, the main motivation is this one. It's not that it can't be. It's just that the main motivation is that scalar boson stars arising as solution to the Einstein-Clairaut equation are stable, horizontally transparent to light. This is the reason why they work with bosonic ones.
It is strange for me because as you said, I think the dark matter surrounding the, the white dwarf, but the motivation is that you can have some scalar boson stars. And so it means some kind of scalar stars, scalar boson stars, to orbiting the white dwarf. Or
I didn't quite understand as well, but I thought it was good I got out. But I didn't understand. I understand the connection between these scalar boson stars and the white dwarfs being surrounded by the scalar. It would be the same thing. They are different things. Sorry.
What are different things?
The scalar boson stars and the case of white dwarf with scalar dark matter surrounding it.
Well, honestly, this was something a bit confusing for me as well when I was reading the paper. I'm not gonna lie. Yeah.
the first time you said this motivation, I think some like a two body orbit each other, and one is a white dwarf, and the other one is the scalar boson star.
Oh, I see.
But as you explain the paper, I think it's just like Patricia said, something orbiting, so it's something dark matter surrounding the white dwarf. So it's strange, little confusing.
Yes,
the
yes.
sequence of the paper with this motivation.
Yes, yes. That's a good point.
I think that if you have fermionic dark matter, in case of light dark matter, spin statistic doesn't let you to agree in the size of a star. But that argument is just for light dark matter. I mean, EP. But here, what's the mass of dark matter?
Let me show the table. When I show the likelihood function, you mean the value?
The
Yeah,
range
this
of
is scalar dark matter. What's the mass of this field?
I think the minus 10.
Yes, 10 to the minus 10, 10 to the minus 11. Those are the best values for the likelihood that they chose. Those ones. The higher this, the better the value. Basically, this is it.
Wait, sorry. So this mu is the mass of the dark matter.
Yes, exactly.
Okay, so if you have fermionic dark matter with that mass, you cannot form a cloud because of spin statistics.
Oh, yes.
I think that's
That's a good point. Yes.
why the scalar is not perfect.
Yeah, okay.
Makes sense.
See that's a better motivation than as is in the paper.
So, this is it. Thank you
Let's
again.
thank the speaker. So thank you for watching and see you next time.